All right, so the last new lesson that we're going to talk about is called volume by cross section. Okay, so if you remember, the last thing we did before was volume. We did volume. We did two types of volume. Disk method, right? It revolved around either revolves horizontal revolves, vertical revolves, and then it created a shape. And then the other one was similar. It was called the washer method. Same thing, except it just had a hole in the middle. Same thing, it revolved, right? But the only difference was there was a part missing in the middle. That was the only difference. We found the volume of those things. Okay. So the last thing we're going to find is volume by cross section. Okay. So first thing, cross section. What is a cross section? A cross section is if I were to take a solid shape, like a solid shape. Let's see. Let's say this thing. Let's see, or let's say my water bottle here. My water bottle is not solid. It's empty inside because that's where you can put liquid in. But let's say this thing was solid. Let's say this thing was 100% solid. I couldn't put anything in there because it was solid. So like a brick. Okay, let's say I took a knife and sliced it through like that. So now I have two pieces, right? And I opened it up. What shape would you see? A circle, right? You'd see a circle here and a circle here. So a circle is the cross section for the water bottle, right? So any two-dimensional shape, three-dimensional shape, you could do that for, right? Any three-dimensional shape you could do that for, and you would see a shape. It's called a cross section. Okay, break it apart. So that's how we're going to find volume here. Okay, these things, these shapes that we see today are a little bit different than the ones we have seen in the past. Okay, first thing is they have flat bottoms. They all have flat bottoms because they don't revolve, right? So you can see the first shape here. They don't really have names for these shapes, but they have cross sections, right? If I were to slice this one in half or anywhere, you'd have rectangles, right? It's a bunch of rectangles stacked together. This one here kind of looks like a cone kind of thing. If you were to slice it there, you'd have a triangle, right? And it looks like an equilateral triangle. All three sides are the same. This one kind of looks like a loaf of bread, right? This one's a little easier because they've color coded it, right? So if I were to slice it, I'd have one of those half circles, right? Half circles. So the cross section would be a half circle. So once you find the cross section, that's what you're going to find area of. Okay? So rectangle, cross section is a rectangle. Area of a rectangle is just base times height, or length times width, right? Triangle, if your cross section is a triangle, base times height divided by 2. Half circle, well, if area of a half circle is just pi r squared divided by 2. Okay? So when it says area of the cross section, first thing you got to do is figure out what shape you're dealing with. And then what is the area of that? Okay? Okay, so they're always going to say, so if it's perpendicular to the x-axis, so if the cross sections are perpendicular, okay? So remember, perpendicular. Perpendicular. So you know what? Let me do it on here. Let me do it over here. So the red is perpendicular to the the red is perpendicular to the y-axis, right? To be perpendicular, you have to cross at 90 degrees. So the red line crosses the y-axis at 90 degrees. So to be perpendicular to the x-axis, I would have to go the other way. So the blue line is perpendicular to the x-axis. Okay? So that's what perpendicular means. Perpendicular means crosses, intersects, but when it intersects, it makes a 90-degree angle. Okay? Okay, so today, one of the big things that we do, these, like I said, most of these are calculator questions, is a picture. A picture. Having a picture in your head, either on the calculator or actually on the picture on your paper so you can draw to figure it out. Okay? Okay, so let's do the first one. Find the volume of the solid if the base is bounded by, so we have this guy, and that guy. And it tells us the cross sections are perpendicular to the x-axis. Perpendicular to the x-axis means dx. dx. Okay. First thing we have is squares. Squares. So the first thing I'm going to do is I need a picture. I need to see what's going on. I want to see the area where it's bounded. Okay? So the first thing I'm going to do is I'm going to go to the calculator. I'm going to go to the calculator and figure out what this looks like. Okay? So let's go to the calculator. Okay, so the first one is the square root of x. Square root of x. So square root x. Okay, that was the first one. The second one, x equals 9. That's a vertical line. And then the last one was the y-axis. Or sorry, the x-axis. The x-axis, you can graph the x-axis if you want, but you don't necessarily need to. We know where it's at. We know what the x-axis looks like. Okay? So I'm going to go up to graph, and there's a good picture of it. Okay? So the red is y equals the square root of x. The blue is x equals 9, and then you have the x-axis there. So that's the picture I want to have on my paper. Okay, so I'll give you some time to draw that on your paper. Oops, I don't want that. There we go. Okay, so that's what it looks like. We're not revolving around anything. It's not like I'm revolving. It's not like the red line is revolving around the x-axis or anything like that. That's what we did before break. Okay, this is a little different. So what it's saying is squares. Each square, so I'm going to have a square. I'm going to have a bunch of squares, actually. Okay, I'm going to have a bunch of squares, and they're all going to be sitting on the blue shaded part, okay? All of these squares are perpendicular to the x-axis, perpendicular. So they're going to cross the x-axis. So they're all going to be standing like this. So picture squares. Picture my hand was a perfect square. It's going to touch the red to the green. So it's going to be slices of squares. Imagine a million slices, a billion little slices of squares. They're all different sizes, right? Because sometimes the distance from the red to the green is different wherever you're at, right? So there's little slices. So this one's going to kind of look like this guy here. Very similar to this guy here. The only difference is instead of half circles like this one, ours is going to be squares. So picture in your head that each of those half circles is squares. That's what it's going to look like. Okay? That's what it's going to look like. So what we have to do is find the area of one of those squares. Once we find the area for one of those squares, it's going to go into our formula right here. Okay, we already know it's dx because it said perpendicular to the x. So that part we know. So we have to find area of a square. So tell me, what is area of a square? Any square. Length times width, right? And what's special about the length and the width for a square? They're exactly the same, right? They're exactly the same. Okay, so if I find one side, I can just square it, right? Or multiply by itself. Okay. So I have each of these guys here. Okay. But again, the squares are not all going to be the same height or the same length or the same width, because the distance from here to here is different than the distance from here to here, right? So these squares over here are going to be small. The squares over here are going to be larger. Just like the half circles at the end are a lot bigger than the half circles in the beginning, right? Okay. Okay, so since they're all going to be different sizes, I have to figure out what the length would be. So we know that the square will go from here to here. So how do I find the length from there to there? How do I find the distance from there to there? So finding the points, right? I don't know exactly where this point is, and I don't know exactly where this point is. But I can find the distance using what? How can I find their distance? Because that'll tell me this distance here. So if I don't know the distance, I know it goes from, so I need a y value here, right? And a y value here. That's all I care about. I don't care about the x's because they have the same x. So how do I find the y value for the top? Let's say I knew the x. X is 6, right here along this line. How do I find the y value?
Finding a point that you know is certain. So like that where the point is, the red point.
Yeah. What would the y value be there? On that red line here.
2.
Not 2. What would the y value be here? I know the x value is 6. What would the y value be? How can I find the y value using the x value? Mm-hmm. Okay. About, right? But we want to be closer than that. You know, we don't want to I don't want to round until the very end if I need to. So how do I find what the y value is there? Plug in 6 to the equation, right? Plug in 6 to the equation. It's the square root of x. So if I plug in 6, isn't that just the square root of 6? Right? So what did I use to find the y value? No. What did I use to find the y value? The equation, right? So anywhere along this line, if I wanted to know what the y value would be here, I would plug in 8 into the equation. Here, plug in 4 to the equation, plug in 2 to the equation, plug in 0 to the equation, right? So if I want to find the y value, I would plug in the x value into the equation, right? That's how you find the distance there. So we use the equation, the square root of x, okay? And then I want to find here. So if I want to find the distance here, what am I going to do? We know how to find the values here. How do I find the distance? Subtract, right? Subtract from the green. Red minus green. Okay, red minus green. So red is the square root of x minus the green, which is 0. And why is it squared? Because if you look in the first page or the top, it wasn't squared. Why did I square it? Because yeah, that's the formula, right? The formula for area is side squared, or length times width, right? Area is side squared. So I found one side and I squared it. Okay. So now I got to find the bounds. Since this is dx, the bounds are going to go from left to right. So where it is the beginning of the blue and where is the end of the blue? 0 to 9. Calculator time. On your calculator, do your calculations. You should get 40.5, 40 and a half. Okay. Okay. All right. So let's look at 1B now on the other side. Okay. Okay, so find the volume. Okay, so this one's a little different. This one's a little tricky. So make sure I stay with me on this one. It's not hard in concept, but it's a little tricky in how we do the calculations because, well, you'll see in a little bit. So find the volume of the solid. So it starts out the same. So right after example 1, the first 2 sentences are exactly the same as the one we just did. So the same picture. Okay, so the first thing we're going to do is we're going to draw the same picture. Okay, so draw the same picture you just have for the second one, for B, 1B. It's the same bounded area. We still have y equals square root x equals 9, and we have y equals 0. We still have those three guys. Still perpendicular to x, so still dx. Oops, don't want that. Okay, so the only difference here is that they're not squares. This time they're semicircles, half circles. Okay, so we're going to have half circles that are going to extend from the red to the green. So the red to the green. So this one is going to look exactly like the picture we saw on the first page. The three examples, the third example that I showed you, that one's, it's going to look exactly like that. Okay? Almost identical to that. The orange line is going to sit on top of the orange. Dot is going to sit there. The other dot is going to sit up here, except there's going to be a million of them stacked. Circles, okay? This is a half circles or two-dimensional shape. Two-dimensional shapes have no depth. So to fill up all of that blue, there has to be an infinite number of them. Okay? Three-dimensional shapes have depth. I'm creating a three-dimensional shape, but a two-dimensional shape doesn't have any depth. So how many circles do I need to sit on top of this blue? Infinite number. Okay? Okay, so the area of a half circle, pi r squared divided by 2, or 1/2 times pi r squared, right? Okay. So if that guy is sitting right there and standing up, half circle, really all we have to find is r, right? R is what we have to find, radius, right? What will the radius be if this guy is sitting right there? So in other words, this is orange dot to orange dot. I need the radius. Is this the radius? Would this be a radius here? Orange dot to orange dot? No, right? What would that be called? Diameter, right? It would be called diameter. Now, diameter and radius, there's a relationship there, right? What is the relationship between diameter and a radius? So if I have the diameter, what do I got to do to find the radius? Divide it by 2 or take half, right? And same thing opposite. If I have the radius, you multiply it times 2 and you have the diameter, right? So what I need to do is I want to use my formula, right? I want to put that in here, except that's not sufficient. That's not going to be sufficient. because I have the diameter. I don't have the radius. So what I want to do is I want to create a new formula that doesn't have r, it has d in it. Okay? So instead of r, what could I put in its spot with a d? It has to have a d in it. That's going to be the same as radius. Yeah, right? What's r? R is equal to d over 2, right? Or sorry. Let me see, what did I do? R is equal to... Did I write it wrong? Yes, I did. This should be 2r, right? 2 times r. Radius is d over 2, right? There we go. So that's what I'm going to put in its spot. D over 2. Because radius equals diameter divided by 2. They're the same. Okay, so now I got to simplify this guy a little bit. Square it. How do you square a fraction? You square the top, you square the bottom. So pi times d squared over 4, right? Okay. Divided by 2. So instead of dividing by 2, what can I do besides divide by 2? Multiply by 1/2, the reciprocal, right? So we take this and multiply by 1/2. So I get pi times d squared over 8. That's the guy I'm going to use. That's the formula for this top guy. What is the formula? How do I, remember I had to subtract, right, to find the distance? What am I going to subtract? The red from the green, right? So on the last one, I subtracted the square root of x minus 0 because the square root of x represented the green, or the red, 0 represented the green. What represents the red and what represents the green? I want to find this distance here. But again, the distance is always different. So I can't just say 2. I can't just say 6. I can't just say 3. I can't just say a number, right? Because it's always different. It's a variable. So what 2 things am I going to subtract to find the distance from the red to the green? No. Because that's because it was a square, right? But so wait, let me see. So yes, so what you're going to do here, so you square root, so the distance here is going to be the square root of x minus 0, right? We said that on the first one. The distance here is the square root of x minus 0. What part of the half circle is that? So that's what we're going to plug in for d. Okay? So we're going to plug in pi times the diameter is that distance. That distance is the square root of x minus 0. Square root of x minus 0 is just the square root of x squared over 8. What is the square root of x squared? X. So it's pi times x divided by 8. That's what's going to go in here. That's where it got a little tricky. Got a little tricky because I couldn't use r, because I didn't have r. So I had to solve for d, use d. And once I got that, okay, what is the diameter? Well, the diameter goes from orange dot to orange dot. Well, since it's a rectangle, or so it's, sorry, since it's a half circle, I have to put that in for d. Okay. Bounds are still the same because it's the same 0 to 9. Uh-huh. Oh, sorry, it's supposed to be 8, supposed to be, switch the 8 and the x. Sorry, yep, you're right. X, 8. There we go. Calculator time. See what you get. Okay, so you should get 15.904. That's going to be the volume of that shape. Okay. All right, we're going to do one more. We'll do C, 1C, and then we'll be done for today. 1C. The reason I want to do 1C is because it's the same graph. It's the same layout. The only difference between 1A, 1B, and 1C is the shape they use. For C, they're going to use isosceles right triangles. Okay? So first thing we're going to do is draw the shape. So for number one, or 1C, draw the shape. So this one is an isosceles right triangle. What do we know about isosceles right triangles? What are the things that we know so far that we're bringing into isosceles right triangles? Isosceles means 2 equal sides. Exactly. That's what isosceles means. There's equilateral triangles means all sides are the same. Isosceles triangle means 2 sides are the same. Third side is different. And then the last one is a scalene triangle, which means all sides are different. Okay, so isosceles means 2 sides are the same. Put that together with a right triangle, what does that mean? You have a triangle with 2 sides that are the same, that has a 90-degree angle in it. So let's draw a picture of one. Okay. So the 2 sides that are the same, those 2 sides are the same. What are the 2 angles going to be? What are these 2 angles? Do we know what these 2 angles have to be? 45. 45, 45. It's a 45, 45, 90. Isosceles right triangles are all 45, 45, 90 because 2 of the sides are the same. And since one of the angles is 90, the other 2 angles have to be the same size, so they're both 45s. Okay. So what that's going to look like is one of these guys is going to be sitting from red line to green line. So that orange line is going to sit right on top of that orange segment. It's going to sit right on top of that orange segment. And there's going to be a million billion of them just lined up just like that. Okay. What is area of a triangle? Area of any triangle. Because area of all triangles is the same, right? What's area of any triangle? Length times width divided by 2, base times height divided by 2, 1/2, any of those guys. Any of those guys work. Right? Okay. Okay, so what do we know about the base and the height for this type of triangle? They're going to be the same. Base and height are going to be exactly the same for this triangle because it's an isosceles triangle. Okay. So we need to find the distance, the length of the base, which is going to be the same as the height. Well, isn't the base going to extend from orange dot to orange dot? What is the distance of that? Square root of x minus 0, which is just the square root of x, right? Which is the same as the height. Well, the square root of x minus 0 is the square root of x times the square root of x over 2. What is the square root of x times the square root of x? X over 2. That's what we're going to put in. The bounds are exactly the same, 0 to 9. Because the base and the height are exactly the same distance on an isosceles triangle. We know the base is going to go from orange dot to orange dot. We know that distance is the square root of x minus 0. That's how we came up with the rest. Okay, so go to your calculator, and you should get 20.25. And you're done. Okay. So we're not going to do this today, but look at number 2. Look at number 2a. Tell me differences. Tell me differences between what we're going to do tomorrow versus what we just did today. This one's perpendicular to the y-axis. So instead of sitting like this, tomorrow our guys are going to be sitting like that, okay? Which is dy. Okay, and then it changes a little bit. You got y equals 9 and y equals x squared. Okay, so the first thing we're going to do is we're going to draw the picture. We know area of a square is side squared, x squared, whatever you want to call it, side times itself. Okay, and then go from there. Okay. All right. Okay, so that's what we'll do tomorrow.